Okay. Hello everyone, welcome back. I hope you guys had fun during the break. As you may have noticed, we have the deadline for assignment 2 is going to be this Friday. Initially it was right after the break, but we thought to extend it not to rush you through things and let you enjoy the break. Okay? Again, I'm repeating this. The midterm exam is going to be October 23rd. Please mark your calendar. It's going to be in the very same class, exactly the same time. Phase 2 of the project has been already posted on Blackboard. How many of you can see? Very good. We're going to have a discussion about it today, but right after we finish what we want to talk about today. Okay? Some of you have been actually asking questions about assignment 2 on Blackboard, and Johan has been responding and have been monitoring this. So far the response rate is good, right? Please, if you have any queries or any questions, please try to ask your questions as soon as possible, not the last minute or the last day of the assignment, right? This would be hard to take a lot of questions by the end, right? Okay, so last time we talked about parallel database systems, and more specifically we talked about how the database system, if we have multiple computers, multiple processors, multiple CPUs or computing units, how can we parallelize the execution of queries in the database system? We looked at the basic definitions of speed up versus scale up, right? And speed up basically is how much, like if you add more resources, you need to, the speed up or the speed of the query needs to increase linearly with the resources you have. And scale up means if you have more data and if you add more resources corresponding to the size of the data that you added, the speed of the queries should be constant, remain constant. Again, speed up and scale up, they're kind of related to each other in a parallel system. And then we talked about in a database system, what does it mean to do parallelization? We said that in a query, as we already talked about earlier in the course, the query is basically you have a query tree, and this query tree, the executor run it. Query tree has several operators that represent the different operations of the query: selection, projection, join. So one way is to, each operator is to parallelize the execution of this operator, right? That's one way. Another way is to make, if you have multiple computing units, ask each unit to run a single operator in the plan, right? So, or another way to look at it is that you have multiple queries come to the system. How can we run them in parallel using different CPUs or different computing units? So this different level of parallelism that we have here. So we're going to take a look today, and then we talked about some partitioning methods. In order to parallelize execution among data, we need to make sure the data is partitioned among the computing units that do the work. So we've looked at round-robin, range partitioning, and hash partitioning, and we've seen which one is roughly is good for which operation. We talked about like range queries, include joins, range joins, all these kind of operations. And then that's how we stopped last time. So what I want to talk about today is like, okay, let's see what are the methods or the algorithms used in parallel database system to parallelize the execution of the operations in the database. This is a question for you guys. What is the simplest operation that we do in the database, in the query? Selection, right? And the selection physically, from a physical perspective, it's basically scanning, right? So you have the data is stored in a table, and this table is actually on disk. Is stored as a file on the file system. So basically, physically speaking, this selection operator, one way to run it is to scan the whole file and retrieve the data that matches the selection predicate, right? That's one way. Of course, there are other ways. You have an index and different ways to do the selection, but one physical operator is the scan operator. So a question for you guys, if I want to parallelize the scan operator, what should I do? Anyone, it's easy. It's not a trick question. Please.
Divide the data.
Okay.
Evenly, probably.
Divide the data evenly, and then each computer, like each processor, will do the scan on its own, right? Perfect. So it's very easy, right? So scanning is actually the easiest operation in the database system. So if assuming that the query optimizer decided to choose scan to run the selection operator, basically you have multiple processors. You do a round robin partitioning, very easy, right? And then you scan. Each processor will scan the partition that it has, and then filter out the tuples that do not satisfy the selection predicate, whatever this predicate is. Okay? Very simple. And then you might have, like at the end, like a coordinator that takes all these results and return it to the user. The final result of the query and return it to the user. Okay? Very easy. What if we have a indices? What if I want to use indices to solve the question, solve the query? Please.
Rate partition. For this number of indexes, I am gonna run this computer.
You can run range or hash partitioning, right? And then for each partition, you build an index. And instead of scanning, you use the index to answer the query, right? So you don't necessarily scan everything. You build the index, and the index helps you filter out based on the predicate. Better, okay? So this is also another way to do it. It is as simple as that. But what if I want to do sorting? Sorting is a major operation in a database system. It's actually a major operation in computing in general. But database systems, if you used SQL before, there is the order by SQL clause, right? An order by basically sorts the data based on a specific attribute in the table and return the sorted order to the user. So this sorting operation, how can we parallelize the operation? Any ideas? Other people? Other people? Don't be shy. You're gonna say it right. Okay, please. You were raising your hand, right?
Well, I was just trying to come up with the specific terminology for it. It's kind of, you take segments of it, you sort those small segments, and then you come back. I forget the terminology.
That's sorted runs, right? Okay. So basically, the idea of sorting is that there are so many sorting algorithms, if you've taken any algorithms in data structure before. But these algorithms work for just simple in-memory programs, right? In database systems, and to parallelize the sorting in general, since you have need to use some kind of partitioning, you may leverage this partitioning method to do the sorting, okay? So what kind of partitioning method can help you out with the sorting? What if I used round-robin partitioning? How can I sort in this case? In round-robin, the tuples are assigned to multiple partitions randomly. I mean, there's no specific way that you can say these tuples represent specific attribute value. So in this case, yes, you can do, each processor can sort the local partition. But then this local partition, even though it's sorted, but globally, you cannot actually come up with a good or the real sorted the real sorting result of the whole data. Why is that? You need another level that merge these sorted runs, right? And another level that merge them again, like you do in merge sort, right? So to do that, this means that you need to, for all the partitions, you need to merge two together and then do sorting again, merge two together, do sorting again, so on and so forth. This can take multiple iterations, depends on the size of the data and the size of the sorted runs and everything, and the number of processors that you have that runs. We can do it in a much easier way, right? So if you use range partitioning, how will this work? The same. So you do range partitioning, and let's assume you want to sort everything. Let's assume you have an employee table, and each employee has an age. Okay, and you want to sort based on their age. Sort this table based on the employee age. So you do range partitioning based on the age. That's step one. And that's one partitioning method we talked about. And then after you do the range partitioning, each CPU or each processing unit will take the local partition and sort it. Now, it's the same as we discussed already. Every local partition has a set of sorted data. But the idea is that you don't need to do the merge sort that we talked about. Why? Because we know, based on the partitioning schemes that we have, that each processing unit, or each partition, actually has the data between a specific range. And these ranges are already known for the system. This means the sorting has been already done at a global level before we do the local sorting. So you don't need to do any kind of merged runs or anything like this. So basically, this is exactly what a parallel sort works, how it works in a parallel database system. Two phases. First phase is range partitioning. Second phase is local sorting. And then you get the results. Everything is sorted easily. Sounds good? All right. Sometimes people will say, like, okay, if I do partitioning can be sometimes time consuming, right? Because range partitioning itself means that you have to scan the data once to do the range partitioning. This is true. So one trick is to, instead of doing a partitioning based on the entire data, is that you do the partitioning based on a sample of the data. So take just a sample. You can use random sampling or stratified sampling, or any kind of sampling techniques. Depends on the data, depends on the circumstance and the application. You take that sample and you determine the boundaries of the range for each partition based on that sample, instead of scanning the whole data every time you want to do partition. So this will save the time of the partitioning a little bit. All right. So we talked about parallel sorting. So parallel sorts. So phase one, range partitioning. And then you have phase two is local sorting. The next question is, how can we do parallel joins? So a join is also a very important operator in the database system. And we've all used it before. If we use SQL, we just put two tables together and you want to merge them, or even more than two tables. When we talk about join, we talk about joining, integrating two tables together. And if you have multi-way join, you do it on different levels. So two tables, you want to join them together, but you want to do this in a parallel fashion. If this is a requirement, how can you do that? Question for you guys. It's easy. It's not a trick also. Please, yeah.
First range partition it and then join the fragments which have overlapping ranges.
So range partitioning based on what?
The key on which we are joining.
So first range partitioning based on the key, right?
Yes.
Let's call it K. And then
based on the range overlaps between the fragments, we can just
so you partition both relations
yes.
based on, if you do near R joined with S, you partition both relations based on the key.
Key.
And next,
Next is now we have different ranges, right? So if one range overlaps with, if the range partition of R ranging from x1 to x2 overlaps with two partitions of S or even one, we join those three together.
what about we use the same exact partition range
Yeah, that also.
for both R and S? So like for example, if R, we partition the key based on values from 1 to 10. In S, we also partition the key from 1 to 10, and then 10 to 20. All of them, they match. So in this case, how can you do it?
You just get the same ranges and join them.
You do the join based on the ranges because you have the same exact values, and you're sure that you're not going to find these values in other partitions, right? So you can do the join locally. You guys think this is good? Will it work? It will work, right? Okay. So the second step is local join. So this, what it did basically is that, yes, we used the range partitioning, and then we applied the local join that we did is basically a nested loop join, right? So nested loop join is basically you do R and S and you go through a loop to figure out whether the two tuples match or not.
Can't we do range and a sort merge? Range and a sort merge.
You wanna suggest another method. So what is the other method to do it?
First partition it and range partition, then a sort merge,
So range partition.
and then a sort merge.
So in other words, let me put it away and let me know whether you agree with this. So parallel sort, the same way we already talked about it. And then this will allow us to do a sort merge locally, right? Yeah. Local sort merge. This one is local nested loop. Which one is better? It depends on,
Second,
no, not necessarily the
there's
case.
a condition. There's a condition in sort merge if the data cannot be sorted and the data is too big, then the sorting is like a.
It can take a lot of time, right? So it depends again on we talked about the optimization, right? It depends on the statistics, it depends on the number of processors we have. So the optimizer decide which plane. But these two planes can work, right? And the optimizer has an option to choose which one of them to use, okay? So local sort, this is local nested loop. Do you guys have any questions? All right. So this is just, we've looked at how to do scan, sort, how to do join, which are the basic operations. Because again, in scan also, you don't necessarily do the scan for the selection. You can use the scan for projection as well, okay, to do the projection of the tape. And for the projection, you can also use sorting and everything. So it depends on what kind of, these are the major operations that the database system really run, even if the query is more complex than that. So if you have complex queries, so how can you do it? A complex query usually is not just one operator like this. A complex query would look like this. So you have a join, okay, and then you have a join here again, You have a join here. So these are nested joins, and then you have here a selection, another selection. And here you have R1, S1, and then you have here also two other selection. So R2, S2. So the query usually looks like a tree like this. So if you want to parallelize that, in like, you can decide what parts of the plan run on which site. So you have multiple sites, you have multiple computing units in these sites. So in this case, you can say, okay, I'm going to partition this plan that way. I'm going to send this to this processor. I'm going to send this to this processor. Or I'm going to send this to site 1 that has multiple processors. And then these two, I will run them in parallel. And each one of them, I'll also do it in parallel. And then the result will be also parallelized. So there are so many options to do that. Okay. So it's not only that you parallelize this specific operator, you also parallelize the execution among all of them. And the decision taken how to parallelize this is again by the optimizer and the cost model. We already talked about the cost model. Notice something, like if you don't have a parallel database system, usually you don't have a plan that looks like this. We call this bushy plan. Okay? We usually have something called the left D plane. The bushy plan is good for parallelization because things, you have two branches, they can be parallelized. But in a centralized system, usually you do left D because you have to do one join at a time. Okay? Also, some operations in the query, we call them blocking operations. Okay? So blocking means that you cannot do pipeline parallelism for them. You have to wait for the answer to get the whole answer from this operator before you feed the output to other operator up in the query pipeline. So in this case, there's no way you can parallelize that. Okay? So there are some operations that allow for pipeline parallelism, some operations that do not allow pipeline parallelism. All right? For instance, if you have sorting, you can parallelize the sorting itself, but the result of the sorting cannot be pipelined, right? Because you need the whole result to take a decision of the sorts. But the scan can be pipelined. Why? Because if you check one tuple, and this tuple satisfies the selection predicate in the scan, you can pass it up into other operators that can work on it, on these set of tuples in parallel with the scan while the scan is still running. Okay? So this is what we meant by pipeline parallelism. So when you have a query like this, it's not only the partition parallelism that we do inside each operator, there's also something called pipeline parallelism. Like operators work in different levels of the tree. They work at the same time on different tuples. Everything is parallelized that way. Any questions? All right. So it's probably not a good time to talk about assignment 3, right? Because you still didn't finish assignment 2. But I'll talk to you about it next week. Okay? So in assignment 3, again, spoiler alert, you're going to implement parallel sort and parallel join. The same way we talked about. Very simple, right? Parallel sort and parallel join. Straightforward algorithm. But we'll talk about it next week. Focus on assignment 2 now. Please.
Can there be a situation wherein even the blocking operation in the bushy join, can bushy join be better than the left-sided join? Like the left in tree, can the bushy join, like the bushy cost model, can perform better than the left side?
Yeah, it can if you have a parallel database system. If you don't have a parallel database system, it may not be.
No, but in a parallel database system, even though there's a blocking operation, so can it perform better like the bushy tree? Sorry.
Yeah, you can perform better. Yeah. All right. Okay, so since we talked about parallel query processing, I want to continue talking about parallel data processing in general, but I'm gonna switch gears to, instead of talking about traditional relational database system, I want to talk about Hadoop MapReduce. Before I proceed, how many of you have heard of Hadoop or MapReduce? How many of you haven't heard of Hadoop or MapReduce? No problem, we're going to talk about it, okay? So, back in the time, I'll say like a couple of years ago, a lot of people raised their hand that they didn't hear of it. Now we have a lot of people. Let me give you a little bit of perspective, like what is Hadoop MapReduce and why it exists. Like, why don't we just have database systems the same way we used to have it for years? Decades. So, database system, as I've already mentioned that to you guys, the development of database systems started in the 60s, late 60s, and the early 70s, and it has progressed. Again, it didn't used to be the same way. We had database system in these, like in early 70s, but it didn't look the same as what we have these days, relational database. Relational database has become more mature, I will say, in the 80s. So it's becoming, since the 80s, relational database looked pretty much the same. The same use models, the same everything, the same connection to the application, maybe a few changes, but not much. And it, again, till like the mid-90s, database system, every single computer system on Earth has a database system running for some reason. Okay, because we had data, like we had banks, we had libraries, we have flight systems, we have all these kind of things. So every single computing or enterprise system used to have a database system running, relational database, till like mid-90s or late 90s. Okay, and then like it came like the late 90s, came like the internet or the internet bubble. You guys heard of this term before. The internet came in the mid-90s, and then a lot of the web has become really popular by the late 90s. And then companies like Google, Yahoo, and everything become really popular. When they started as just like advertising, and people were looking at them that way. But by the late 90s, early 2000s, these companies has become actually one of the major companies that are driving technology across the world, right? Technology, information sharing, information retrieval, all these kind of things. And you guys can see that now. Like Google is like everything, right? So it didn't used to be like late 90s or something like this. So if you were not a kid, late 90s, you will remember these days, right? Anyway, so when Google came, right? Google, when it started, Yahoo, when it started, they used to use a relational database system, okay, to store the data and retrieve the data from the user, from the queries and everything. Over time, the data coming in has become really, really huge. So when Yahoo started, the web was not that big, right? And all the search engines, indexing the web and storing the web was not like a major issue, right? Because the data was very little. But as Google joined the business and has been indexing every single information on Earth, not just web documents, this data has become really, really big. And also, the web has become more popular, right? and this make the data even bigger. So everybody has a website these days, right? And every not only a website, you have more complex information that is shared on the web. Not only the size of the data has become big, but also the structure of the data has become more complex, and the ability of the existing database system to digest this size of data and this kind of variety of the data has become really hard. So in consequence, companies like Google started thinking about different systems to store and process the data, okay? And since these systems did not exist, like Oracle, for example, didn't support such system, or Microsoft SQL Server, or any of these systems, so Google said, okay, I'm just going to step in and develop a system that will work for the workload I have. Google is a big company, and there are so many different things that Google work on. And there are so many different workloads inside Google itself. I'm not talking about the query retrieval or the search query that you pose to the system. No, I'm talking about inside. To serve you, there's a lot of analytics that goes on in Google, okay? So one of the very simple tasks that Google did, and still does, is you guys search every search keyword, or like keyword search we all do, it's stored in a log file. Every single thing. So whenever you go, and you search for something, this is stored in a log file, the timestamp with a lot of information, right? So this log file is huge. You can imagine why, and specifically that everybody's using Google now, so this is beyond your imagination, right? So Google figured out that they don't have a simple system that allows them to just simply parse this file and organize the data in it. Just the simple task of parsing the file was difficult for Google. So what they did is that they said, okay, I want a very simple software infrastructure that allows me to massively parallelize the execution of a parsing document and massively parallelize very simple tasks like do aggregation, collect statistics from this huge log. So how can I do that? At the time that Google started doing this, thinking about this problem, relational database system, the biggest scale of the system back in the time, it used to run on like what, 20 machines, something like that. So which wasn't so big. The biggest relational database system also at the time used to at most hundreds of gigabytes of data. This is the max back then. And the data that Google had was way bigger than this. And the workload that Google had was not just to run SQL queries, is to basically do some parsing over non-relational data. It was pure text, and run statistics on this data. So Google engineers realized the problem, and what they did is that, okay, we're gonna take these requirements, and the requirements are basically, you don't have relational database, you have just files. So unstructured data. So it's unstructured, and sometimes it may have some sort of structure, or maybe semi-structured. So, but the assumption is that I'm assuming it's unstructured. And the data is so big it's so big that a single computer cannot solve the task. It's so big that just a few computers cannot solve the task. So I want to massively parallelize this across dozens, if not hundreds of machines in order to scale. And I want a generic programming API. What it means by generic programming API is that this kind of program that runs on this massive data, unstructured data, should be defined by the application developer. So the application developer can say, I have this logic, and I want a programming API that allows me to write this logic. And once you write the logic, it needs also to be very transparent. So this means that all the parallelism details and all the system details should be isolated from the application developer. So all the application developer needs to focus on is the programming API that helps them achieve that task. What is the kind of, like, again, we talked about parsing. What is the kind of thing that Google, why would Google need parsing the document, this log file? So if you look at a task like this, so this is the log file, and then whatever kind of search, you search soccer, and then there's another one that has football, and then Goldie. You guys know who Goldie is? You watch baseball? Okay, so Goldschmidt. It's one of the players in Diamondbacks. So there are so many of these, and then there's soccer again. So this is a huge log file. Basically, what you want to do, the task is to take this log file, parse it, and for each word, count the occurrences of this word in the log file. Very simple task. So the output of the task is basically, you say, okay, these are the words that exist, soccer 2, and then football 1, Goldie 1. Okay? So that's very simple, right? So why would Google use that? Google used that to actually use the search keywords and how many times they appear, or even in the documents, the web documents, to decide the page rank, right? It uses statistic as part of the page rank algorithm. Okay. Very simple, but the problem again is this is not a relational database, and it's so big. How can you do that? So what the engineers at Google, they figured out that you can do this in very simple, in 2 main steps. One step is to read the files, read this file. Again, the assumption is this file is partitioned across multiple machines to massively parallelize this. You read it, each partition, and then each local, whatever processor, it does parse the file that it has locally and then count. And whenever it encounters a word, it says soccer. And if another file encounters the same word, they don't communicate together. They just read the whole word. So the other processor will say also soccer. And all of them will do this at the same time, right? Because they don't have to be related. Everybody reads the local partition. So that's the first step. So did I solve the problem? No. But what I got, the information I got from this, is that each single processor managed to parse, do the parsing step. And not only this, it figured out, like the logic defined by the programmer is to find a word, and for each word, just say, I found it in my local partition. And if I found it more than once in my local partition, I'll say, so if I found it twice, I'll say 2. And every file will do that. The second step is the aggregation step, that you want to also, all the outputs of every single processor is to be aggregated together. So if you have two processors that find the word soccer once, so the second phase is to take the output of soccer together and say, okay, I found soccer 1 and 2, so say 1 plus 1 equal 2, and this will get you the final output. So this simple logic, again, this is a very simple program. You can define more complex using this paradigm. So the first step is called map. And the second step, the aggregation step, is called reduce. So engineers at Google, they figured that using map and reduce, you can basically define a wide range of programs that can run against a system that can massively parallelize the execution. So this map, these are two functions, and these two functions have the same interface, and the application developer runs code inside these functions. But the code takes the same input and the same output. So the output of the map is a key value pair. So the key in this case, for instance, is the word itself, which is soccer. And the value is 1, which is I found it 1 in my document. So each map, so this map is a parallel. So you have 1,000 of these map programs running at the same time on multiple machines on a partition file. So it runs in parallel, and each map process returns a list of key value. So key value. The reduce takes as input also a key and a value, a set of key values, and then return finally also key value. So why reduce takes as input a key value list? Because to match the input of the output of the map, between the map and the reduce, the system internally has kind of shuffled the data around across multiple machines to make sure that each reduce task takes data that has the same key. So in this case, the shuffle phase is automatically implemented by the runtime of the system. So it shuffles data around and puts each reduce takes everything that has soccer in it. Okay? And then another reduce takes everything that has football. Another reduce takes Goldie. And then based on that, this shuffle phase that happened automatically by the system, the programmer who wrote the reduce task will just do some kind of aggregation on top of this data. So in this case, the aggregation is just summing up all the occurrences of the words. But of course, it depends on what kind of application the programmer needs to write. So Hadoop map reduce, this is basically what it does. So to do that, of course, the system assumptions are that you have dozens, again, if not hundreds of machines, and each machine can run as a mapper or a reducer. It's fine. So MapReduce, the program that you write in MapReduce, it's a single MapReduce. I mean, there is version 1 prototype implemented of it, or like a version implemented of it in Java. It's called Hadoop. So Hadoop is implemented by Yahoo. It's based on the idea of Google, and then they took it and open sourced it. So you run one Java program that has the map and reduce. So these are two functions. And this Java program is sent to all machines in the cluster so that each machine can actually run a map or a reduce. The only condition is that the map runs first And there's one map phase and it has to finish first. And then comes the reduce phase after it. So you have multiple workers, worker machines. You run the map phase, you do whatever needs to be done here, like the example we talked about. And then map phase ends. The system does the shuffling across the cluster. You have multiple workers. The shuffling happens automatically. And then the reduce phase starts after that. There is one master node, and the master node, the program originates, the MapReduce program originates at the master node. The master node keeps tracks of which worker is doing its work, or which worker is kind of stuck somehow, and it takes decisions. It oversees the execution of the MapReduce program. So again, you have one master here, and then this master sends MapReduce tasks to the workers. The workers run the map, and then there is a shuffle phase, and then there is a reduce phase that's also among the workers. And then the output of the program is returned. To do all of this, you need a very reliable distributed file system. This is why, again, in Hadoop, there's something called the Hadoop file system. It is a distributed file system that you partition, like the original log file that we were talking about. This is stored in this file system in partitions. It's distributed, and there are several partitions of it. And the map, when the map phase runs, each mapper runs on a partition on this file system, on the file specified. The file system is not only useful to store the input data and the output results. It's also useful in the middle of the execution of a MapReduce. So in the middle of the execution, each map phase, after it finishes the task, it stores the intermediate results on the Hadoop file system. And the reason behind that is for fault tolerance. What do I mean by this? If the mapper fails, that's all right. You're going to run the map again on the input file that this mapper works on. But if the reducer fails, one of the reducers, you have thousands of reduce processes running across hundreds of machines. If one of them fails for some reason, so what's going to happen? You don't fail the whole program that has been running for days, for instance. You actually can, if a reducer fails, you stop that reducer and you initiate another reducer on the same piece of data retrieved from the map. This is why the mappers store the results on the Hadoop file system. So this is good for fault tolerance. So fault tolerance is also, happens if there is any crash. Please.
I'm just curious, more speaking on this kind of fault tolerance bit. I understand that they separate files based on some default file size, right? To different
Yes.
blocks. Now, is there any redundancy to those? Say if they split a file into 3 blocks, is there any redundancy
Yes.
of those 3 blocks?
It's a good question. So another way to achieve fault tolerance, and this is actually in Hadoop also, is replication. So data in the Hadoop file system is replicated across multiple machines. And this is one way to achieve fault tolerance if, for example, the mapper on one machine fails, or the machine itself, for example, goes offline. So you have the same exact partition or the same exact block replicated on another machine. You can start and do the same exact task. Good point. Other questions? Please.
Can you repeat how reduce works parallel along the different operators? Because it has map has different outputs.
Yes.
So soccer can have in many data and in many map data in different data.
Yes.
So So how
Good
it
question.
changes
So
it
the
falls?
mappers finish. Once the map finish, the reduce phase doesn't start right away. There is a phase in the middle. It's hidden from the programmer. It's not by the system. It's called the shuffle phase. So the shuffle phase basically looks at the output of the map. The output of the map is key value pair. So sort and group the keys that are similar and shuffle them around on the network, across the network, to put them on the machine where the reducer will start. So that each reducer will get data with the same key. In this case, reducer 1 will get soccer. So it can take it can easily aggregate all the soccer data. Reducer 2 will take football. So it will aggregate all the data with football. So in this case, this hidden phase, it's automatically done by the system, and that's one reason why we have this key value output, and this key has to match the key. The programmer knows that the output key of the map phase has to match the input key in the reduce phase. All right?
So actually, those transformation is like serial or that will be also like kind of parallel. So putting it.
Yes,
coupling the
reducers
data-
will work in parallel because you have multiple. You have soccer, you have football, you have Goldie, so all of them will do the aggregation in a parallel fashion as well. Yeah. And again, so the input and output is a key value. Key value is very generic. This key can be anything you define as a programmer. And the value also. It can be a string, it can be an integer, it can be a mix, right? And the value can be like text, can be any kind of thing you define. It's very generic that allows you to define your own logic. And this is just one example. Any other questions? Somebody has a question here. Please.
So this can be done using relational DB as well, right?
This can be done in relation database, yes.
So why this one? Why not this?
First of all, this is unstructured data. Second of all, when they did that, back in the time, there is no parallel database system that can run this at scale. But it's an interesting question. Actually, in 2009, there's a paper by several authors in the database system. Yeah, so I'm not going to mention one of them only. But the idea is that they looked at MapReduce, Hadoop MapReduce, and they also compared it with state-of-the-art parallel database system for several workloads related to relational database. And in that paper, they proved that MapReduce or the Hadoop MapReduce is not actually good all the time. But there's a caveat here. In this paper, what they did is that the number of machines used are still limited. They used, the maximum I guess they used was like 50 machines, something like that. While Hadoop, Yahoo, for example, and Google, they claim to run MapReduce on 1,000 machines, commodity machines. Remember when we talked about scale up for shared nothing architecture? We said that their system is a shared nothing architecture, MapReduce, and there are shared nothing architecture database, relational databases as well. But the shared nothing architecture of Hadoop is way more simplified, and the existing implementations are way more are easier to scale than existing implementations of relational databases. But yes, the task can be implemented in a relational database. But think about it. This is more generic than a relational database somehow, because you can run more complex programs. This is basically a programming API. It's not just a SQL input and relational tables and tuples, and it doesn't have this kind of strict schema, right? So even if you can scale a relational database, it will not scale the same. Also, another difference between MapReduce and relational database is that relational database systems were designed to interact with the user, right? So it's an interactive workload. What does it mean? You have queries, and you have also transactions, and you have a lot of things. This doesn't do any transactions or anything. All it does is like you have humongous data, and you have some kind of logic you want to run on this huge data, and you want to just massively parallelize this. That's what it does. But there is no notion of transactions, there is no notion of integrity also constraints or any kind of the consistency or any of that. There is fault tolerance, but the fault tolerance, the reason we need fault tolerance here is to make sure that whatever work that has been done to process the MapReduce job, it's not going to be wasted. If, for example, there is a crash or there is a failure or there is anything, it can proceed from a point, not from scratch. But there's no such a thing as, again, consistency or any of that at all. Interestingly enough, after this was invented, it was just designed for this specific task. So people started to think about, oh, how can I add transactions to it? How can I add, but this is again, like it's kind of a plumbing work. So people got excited about it because it scales, it amazingly scales to do these kind of specific tasks. So they said, okay, I'm going to replace relational databases with Hadoop MapReduce. And that, of course, is wrong because they're not the same thing. Yes, sometimes they can do the same task, but that doesn't mean they're exactly the same system. Okay, they have different purposes. Other questions, please.
So here, like according to those examples, like every user will be having one key value pair, for example, the software and football. So like when you are looking into a huge log file, there are like so many words and so many key value pairs. So is it possible that is it necessary to have like one key for one reducer? You can have multiple keys for one reducer.
You can have multiple keys for one reducer, yeah.
And one reducer is not to be like mapped to one local system or one reducer. One can have many reducers. We can scale it.
Yes.
Program it.
Yeah. You can identify the number of reducers, the number of maps. You can add more machines, and hence you can decide how many reducers or how many mappers run on one machine, right? You have all these kind of, that's the architecture of the system is so flexible it allows you to do all of these kind of things. And that's one of the benefits of MapReduce, and one of the main reasons a lot of people adopt Hadoop MapReduce, right? If you talk about big data these days, people require that you have knowledge of Hadoop MapReduce somehow, right? Later in the course, I'm going to talk to you about, like, it's not Hadoop MapReduce as a classical way we talked about. It's not there anymore, and I will talk to you about that later. But this is more of a philosophical discussion. I don't want to bother you with this now, but we'll have to talk about it. All right. I wanted to talk to you about the project phase 2. I want to give you time to talk about that because this is crucial. First of all, let me ask you a question. What did you guys think about phase 1? How many of you think they should get full mark on phase 1? This is good. I believe it's good that you guys believe that because it's easy. It's not wishful thinking. You guys sure that you did what's required, right? And what was required in phase 1 was very simple. The idea is that starting from the early in the semester, I've been asking you, okay, play with Apache Spark. Get your hands dirty. But I mean, a lot of people ignore it. They're just like, oh, they're a crazy professor talking all the time or something like this. Like, I'm just going to ignore him now and do it before one day before. Okay, it's fine. So this is why phase 1 was to ensure that you guys really play with Apache Spark, and more specifically, play with this system that we have called GeoSpark. Okay? GeoSpark, you're not going to do you're not going to deal with GeoSpark. You're going to implement your own system. Phase 2, what is it about? Is that we got some functionalities, the same functionality that you implemented and you run in phase 1. We got these functions and we wanted you to implement them, but in Spark SQL. Let me give you a little bit of perspective of how Spark started anyway, right? So we talked about MapReduce. We all know now, we've seen how MapReduce can scale and what is the programming paradigm, roughly. People, when they looked at at MapReduce or Hadoop MapReduce, a lot of people thought there is a problem with it. Two main problems. One problem is that the API, even though the claim is generic, it's actually not generic enough. A lot of the operations, a lot of data mining and machine learning operations that you want to run on big data, it's not easily implemented using MapReduce. And the reason behind this is that in machine learning and data mining, you need to iterate over the same exact data so many times to find the global optimum. Okay? I'm not going to talk about the machine learning details. This is one of the main problems. And to do this kind of iterative analysis or iterative programming, it's not easy to do with MapReduce. To do it, you actually have to run multiple MapReduce jobs to represent each iteration. And that's a pain. It's slow and it's a pain. Not only this, one other aspect that makes MapReduce, even though again it was good at the time and it really parallelized things, but there is one issue, is that every single intermediate result you have to write it on a new file system, which is a disk, it's a distributed file system written on disk. The problem with this slows down the processing. So if you have a lot of data, not only this, if you have a lot of computation on this data, it will take a lot of time still. So there are other issues, but these are the two main issues that made a research group in Berkeley think about how can we develop a new system that overcome these issues. So this is why they implemented Apache Spark. So I witnessed the early days of Apache Spark and before it came in. So the idea basically is that first thing is define a more generic programming API or richer programming API. And they also overcame the challenge of writing everything to Hadoop MapReduce, to the Hadoop file system. So how they did that? They still achieved fault tolerance, but they introduced a new concept. And this concept, they load all the data in the memory of the cluster. So this means in the RAM. But each piece of each partition remembers how it was created. It carries information about how its lineage, its provenance, how it was created. And this information is used for fault tolerance. So if you have any failure or any crash, this information is retrieved to decide how to trace back the computation instead of rerunning everything from scratch. So it is fault tolerant, not as fault tolerant as, of course, is writing things on Hadoop file system, but it still has very good fault tolerance. You don't need to start things from scratch. And it runs in memory, so it's way faster. You don't have to go do many trips to the file system. So this is how Spark started. And you guys have played with it a little bit, which is great. You got how it runs, and how there is an RDD, and how this RDD works, and how to run actions and transformations on the RDDs, and all these issues. In the project, you also went one step further, and you tried an extension to it called GeoSpark. And GeoSpark, again, it's the same as Spark, except that it runs on geospatial data. Okay, and you've seen examples of this. What you're going to do in phase 2 of the project you're going to implement basically 4 main operations. One of the extensions of Spark is called, when people also started developing Spark, they thought about what are the use cases that you can have. Some use case is the same, the classic MapReduce use case. So we've seen this. So they have map and reduce interface. But other use cases are relational database. Okay? Relational queries, relational algebra and SQL. So this is why we implemented Spark SQL. And it's one way to run SQL on data loaded in a Spark system. There is a notion called the data frame, and the data frame it extends the RDD. It's an extension to the RDD to support the relational scheme, like tables and tuples and attributes, and you can do selection, projection, you can do join, you can do everything like this. And this is already implemented and it's there. There are other extensions to it to do machine learning. There's a machine learning library. There's a graph processing library there, streaming library. So we're just going to focus on the SQL part. In the SQL part, you're going to implement, in phase 2, you're going to implement functions, user-defined functions. And these user-defined functions will help support some of the same functions you already ran in GeoSpark. GeoSpark does not run with Spark SQL. It runs with the native Spark RDB. In phase 2, you're going to load the data. Instead of loading the data into an RDB, you're going to load the data into the data frame. And you're going to load the location attribute, location which is long and lat, into one column of the data frame. The location can be either one point location or a rectangle location. And the functions you're going to implement are very simple. So one major operation, again, in the database system is a selection. And the geospatial extension to the selection is to select all objects in the database such that these objects lie within an input range query. This range query can represent, for example, the boundaries of Tempe. You want to find all points of interest within the Tempe area. It's a selection, spatial selection, called spatial range query. To do that, you're going to implement something called st_contains. This st_contains would be, it's a user-defined function, the same way SQL works with user-defined function. So you're going to call it from a select from where. So in the from, you specify the data frame that has the location attribute. And in the where clause, you say st_contains, you give it the range query, the boundaries of the range. And such that the point attribute in the table, which represent point of interest, for example, is within. Like this range query contains this. So the implementation that you're going to do for st_contains will be fed into a query like this. An example of this is actually provided in the instructions for you to do the assignment. Another function you're going to implement is called st_within. It is similar, except that instead of giving a range, rectangular range like this, you're given a point, and you're selecting from all the objects, all the point objects that are in the data frame, you're selecting all the objects that are within 10 miles of this point. So this 10 mile is an input to st_within. So here you say st_within, you give the point, location, long and lat, and you 10 miles. And st_within is actually in the where clause. That's a condition in the where clause. All right? And then you're going to use that to do not only range query, you're going to use that to do joins with the same exact functions that you implement. These functions are actually standard we're not inventing. I mean, the naming convention of these functions is we got this from the Open Geospatial Consortium, and there is a relational database system called PostGIS. It's an extension to Postgres that has functions like that. But you're not going to do this in Postgres. You're going to do this in Spark SQL. So you're going to implement these. You're going to implement the SQL. You're going to run this with the SQL query here, and you're going to also do joins on it with the same conditions. Sounds good? So this is what you're going to do in phase 2 of the project. And what we're going to, now we are actually setting up the cluster. We're going to have a big cluster. And this big cluster is going to be shared across all of you. The big cluster, we're going to load the data. The basic data we're going to be working with is the New York City taxi data set, past taxi trips. And you're going to run these queries. It's a 200 gigabyte data. So it's big enough for you to experiment with. And you're going to run this workload on it. More details about the specs and everything is in the document. Please read it carefully. The deadline for this is the end of October. So it's 1 week after the midterm. So this means you need to start as soon as possible. It's not hard based on the size of the group. If you have good management within the team, you can finish this. That's all I want to talk about today. Thank you so much. I'll see you next week, right?
Hi, Professor.